welcome to a video about absorption. So we've been looking at emission in our previous video. So that's when a low density gas emits light of given wavelengths once it's excited and it's coming back down from its excited state. With absorption, this is the discrete wavelengths that a gas which is cooled will absorb. So when light is passed through this gas, there'll be particular frequencies that are absorbed by the electrons that then move up to different energy levels. So when light with a continuous spectrum is incident on a gas of an element, discrete frequencies of light are absorbed, resulting in a line absorption spectrum. The frequencies of the absorption lines are a subset of those in the line emission spectrum of the same element. In stage 2 physics, you need to be able to describe the line absorption spectrum of an atom, for example hydrogen. You also need to be able to, on an energy level diagram, draw transitions corresponding to the line absorption spectrum for hydrogen. You need to be able to explain why there are no absorption lines in the visible region for hydrogen at room temperature, and you need to account for the presence of absorption lines, which are called Fraunhofer lines, in the sun spectrum. So they're just called Fraunhofer lines when we're talking about the sun. So they're your success criteria. Those 4 dot points, we'll cover them off in this video. So we'll start with a definition. As I just touched on before, absorption is when a continuous spectrum of light is passed through a cool gas and some wavelengths are absorbed. These appear as dark lines on a detector. So like an emission spectrum has single discrete colours or discrete wavelengths of light on a detector, an absorption spectrum has discrete wavelengths, removed from the entire continuous spectrum. The gas generally has to be cool, so it's not already excited. So generally, if a gas is heated, the electrons will be in higher energy states, the atoms of the gas will be excited, and if you pass light through, then the light won't be absorbed because those electrons are already above their normal energy level. A line absorption spectrum is the spectrum that appears on a detector as analysed with a spectrometer. So a spectrometer is something that separates light into its constituent wavelengths. The line absorption spectrum is a spectrum appearing on a detector as analysed with a spectrometer with those dark absorption lines. So it's the incomplete continuous spectrum because certain lines, or certain wavelengths rather, have been absorbed by the atoms in the cool gas. The absorption lines correspond with the wavelengths absorbed by atoms or molecules from the continuous spectrum. So the absorption lines are these missing wavelengths here. And the absorption spectra is a subset of the emission spectra. So what that means is that for any given gas, the wavelengths that it absorbs are definitely going to be included in the wavelengths that it emits, but there could be extra wavelengths that it emits that it doesn't absorb. So the absorption line spectrum or the absorption spectra is a subset of the emission spectra. In our graphic here, we've got some light of a continuous spectrum being passed through a cold gas, and then that light is then passed through a prism so that the light separates out into its spectrum, and then it's viewed with an eye, but with an eye through a spectroscope or spectrometer. And when the eye is viewing this through the spectrometer, this is an example of what the eye would be seeing. So some of those wavelengths missing because they've been absorbed. This technique can be used to identify elements or compounds in an unknown sample. So if you're not sure what's in a sample, if you pass some light through like a gaseous version of this sample, then certain lines will be absorbed, and those lines will correspond with a particular element's absorption spectrum. The sample could be made up of numerous elements, so you'll get the overlapping absorption spectra. So basically you'll just have however many sets of absorption lines corresponding with each element that is present. You can also compare the absorption spectra of stars and planets with the emission spectra of elements, and this will help you determine their atmospheric composition. So now we're going to look specifically at hydrogen. For hydrogen, the absorption spectrum contains 4 lines at wavelengths corresponding with transitions from the second energy level for electrons, so N2 to N equals 3, 4, 5 and 6. So from energy level 3 to 2, energy level 4 to 2, energy level 5 to 2 and energy level 6 to 2. And that is indicated in this diagram here. This is temperature dependent, and this is because hydrogen atoms are in the ground state at room temperature. But electrons must be in the first excited state, which is N equals 2, because the ground state is N equals 1. So they must be in this excited state to be able to absorb photons in the visible spectrum. So what this is saying is that if you were to pass light through a cooled sample of hydrogen gas, the energy that would be absorbed from the light would have too high a frequency, so it would be too high energy to be in the visible spectrum. So it would be like UV, kind of in the UV range, so beyond what the eye can see. So this does contrast a little bit with what we were talking about on the previous slide with gases needing to be cooled. For hydrogen, this doesn't work because then you're not actually able to view the absorbed energy because it's not in the visible spectrum. So the spectrum that you'd have here, if the hydrogen gas was too cool, then lines wouldn't be absorbed, and you just have a complete continuous spectrum because the lines that would be absorbed, or the wavelengths that would be absorbed, would be in the UV section. So by increasing the temperature, we're increasing the energy of the electrons so that they transition to the first excited state in N equals 2, and then they're able to absorb wavelengths of the visible spectrum. So now we'll look at Fraunhofer lines. These were investigated and described by a German physicist called Joseph von Fraunhofer around 1814 or 1815, and these are absorption lines in the solar spectrum, so the sun spectrum, due to wavelength absorption by elements in the sun's atmosphere. So the sun is obviously a source of light, and there's different elements that are present in the sun's atmosphere. So when the light is passing through these elements, they absorb wavelengths of the sun's continuous light spectrum. So these lines appear in the sun's absorption spectrum. It was subsequently noted that Fraunhofer lines correspond with the emission spectra of some element. So at first it was just like, oh, why are there these lines in the sun's absorption spectrum? And then it was like, oh, hey, some of these are matching up with known absorption spectra of elements. So it was able to be deduced that hydrogen, helium, oxygen, sodium, magnesium, calcium, mercury, and iron are all present in the sun's atmosphere. And in this image here, you can see which particular lines correspond with which particular elements. This technique has been used to investigate the chemical composition of stars, planets, and moons. So each of their spectrums would be missing particular lines corresponding with elements that are present in their composition. So now I'll take a quick look at fluorescence. So when an atom absorbs a photon, it is elevated to an excited state, which has a higher energy. Excited states are generally short-lived, and the atom returns spontaneously to its ground state, often by emitting a series of lower energy photons. Fluorescence is the process where an atom absorbs a photon to reach an excited state, but then reverts to the ground state, emitting two or more photons with lower energy and lower wavelengths. The expectation is in stage 2 physics that you'll be able to draw on an energy level diagram of something like hydrogen the production of multiple photons via fluorescence. You'll also need to be able to analyse and explain the characteristic wavelengths, fluorescence, and line spectra for elements other than hydrogen using electron energy levels. So as I just touched on, fluorescence is the process of an atom absorbing a higher energy photon and reaching an excited state before reverting back to the ground state via the emission of, and it has to be two or more photons, and they'll both have lower energy and longer wavelengths than the original higher energy photon that was absorbed. And the reason that both photons will have lower energy and therefore longer wavelengths is because the energy of this higher energy original photon is being broken into two parts, or divided into two parts rather. So those two photons that are emitted, if you were to combine their energies together, they would be the same as the original photon, but because they're being divided, the energy of each constituent photon or each emitted photon is less. It could be more than two, but it has to be at least two. With hydrogen, fluorescence only occurs if a photon raises an electron above the n equals 2 level, so the first excited level, and this is because only one transition is possible for an electron to return to its ground state. So if you imagine hydrogen absorbing a photon and raising up to n equals 2, so the first excited state, the only possible way for this photon to return, the only possible way for this electron to return back to the ground state is by the exact same path. And so a photon with the exact same energy and frequency and wavelength is going to be emitted. If, for example, a photon was absorbed by a hydrogen electron and it went all the way to, I'm going to say, n equals 4. I'm a little bit over 4, but that was my intention, just to hit n equals 4 there. Then it's possible, clicking the wrong button, it's possible for the electron to emit a frequency that corresponds with n4 moving to n3, and then n3 moving to n2, and then n2 moving back to n1. So there's 3 different photons that it can emit that will, their energies collectively will add up to the original photon that was absorbed. And these photons that are emitted have different wavelengths, and so they've got different colours if they all happen to be in the visible spectrum. This occurs in living and non-living things, with applications in medicine, mineralogy, forensics, molecular biology, and counterfeit detection. So for example, in gel electrophoresis, so when you're separating out fragments of DNA, a fluorescent dye is used to mark those bits of DNA. If you're searching for a particular fragment of DNA, so like a particular base pairing code, you can mark that with a fluorescent marker. Fluorescent markers are also used in microbiology, so you can insert fluorescent DNA into bacteria that will result in fluorescent protein being produced, and then those bacteria will then produce that fluorescent protein. That indicates that the DNA has been successfully inserted into their chromosomes or their plasmids, and you can use fluorescent markers in other sorts of protein investigations too.